so let's just review again the different kinds of growth. So we have constant growth. We'll review from yesterday, or from Wednesday, that was dy. No, let's do dp. dp dt, the growth of the population, is just k. That's a constant growth. Then you've got the exponential growth. That was your homework last night. And that's where dp dt is proportional to the population by kp. And then we've got logistic growth, which we started the proof for. We worked through that really long, complicated proof. So dp dt equals kp, and then times the limiting factor of 1 minus p divided by m. Okay, 1 minus p divided by m. Okay, so that's what we had, and we kind of proved all the way out that what that turns out to be. So let's do some actual real life problems. So remember, the logistic levels off at that m. Okay, it caps off, it won't grow anymore. It gets to the top. All right, so let's suppose a population has initial condition of 0, 10, and growth rate dp dt equals 0.01 over 100 p times 100 minus p. Okay, so now we're ready to go. Now, the way that that growth rate was just given to you is, does it exactly match the format of the definition of the logistic growth? Okay, what's wrong? It should be 1 minus, not 100 minus. So how can I readjust that so that it's in the right format? I'm going to not divide by 100, I'm going to factor out 100. Okay, I'm going to factor out 100. So that's going to give me dp over dt equals 0.01 over 100p, and then I'm going to factor out 100. That will leave me with 1 minus, okay, what will it leave me with? 1 minus what? Okay, p over 100. And then the yellow 100 that I factored out, I can simplify, and it can reduce with the 100 that was already there. So I've got 0.01p times 1 minus p over 100. I can tell, now that it's lined up in the right place, what the different variables are. So I know that this is k, and I know that 100 is my maximum. So I've got my k and I've got my maximum all set up there. And I have my initial condition. All right, let's separate and integrate and figure out what the values are. Now, when I separate and integrate, I actually prefer to do it back in the original form, where it's 100 minus p. I like to do it better that way. It's kind of up to you, I guess. But when I separate and integrate, it's going to look like this. dp, oops, change my color. dp over the p and the 100 minus p equals the 0.01 over 100 dt. So I just separated all the p's to the one side and the 0.01 over 100 to the other. And now we're going to integrate. And so our integration is going to be a over p plus b over 100 minus p, all dp. And that's going to be equal to the integration of 0.01 over 100 dt. So we'll need our integration by parts. So we'll multiply p by 100 minus p, or a by 100 minus p, and then we'll multiply b by just p. So we'll have 100a minus ap plus bp all over p times 100 minus p. So I'm doing my partial fractions. And that has to be equal to the original partial fraction. Slide this over, which was 1 over p times 100 minus p. Okay, can you figure out what a is supposed to be? 1 over 100. So then what will b end up being? Okay, they'll be equal. All right, so my integral is now 1 over 100 over p minus 1 over 100 over 100 minus p, still equal to 0.01 over 100 dt. I think I would like to pull 1/100th out to the front. That'll just leave me with 1 over p and 1 over 100 minus p dp. And I'm also going to pull just the 1 over 100 out from this side, which leaves me with 0.01 dt. If I can pull 1 over 100 out of both of them, yeah, so that's going to be simpler for me. What did I do? Oh, it's not. Thank you, Eating. Okay, so now we're ready to do our antiderivatives. So we're going to have the ln of the absolute value of p plus the ln of 100 minus p plus the constant, all equal to 0.01 t plus the constant c. And now I can figure out my constant c because I know my initial condition. Right? The initial condition is 10. So I'm going to have 0.01 times 0 plus the constant, and then the natural log of 10 plus the natural log of 90. And so c is the natural log of what if you put 10 and 90 together? 900. Okay, so that's my constant. Because remember, with logs, you can add them. Or if you can add the logs, you multiply the quantities together. So we have the natural log of p. I'm going to drop the absolute values because I know that it's going to be positive. Equals 0.01 t plus the natural log of 900. Okay, one way to do this is to get all the natural logs on one side. So we have natural log of p plus the natural log of 100 minus p minus the natural log of 900, and that would all be equal to 0.01 t. If I pull all of those over to the other side, I can use the rules of natural logs. The rules of natural logs tell me that I can multiply p times 100 minus p squared over 900, and have that all be one single natural log. And to have a single natural log, it's easier for me to solve. So I can use e now to solve that. So 100p minus p squared all over 900 equals e to the 0.01t. Then you can cross multiply, and we're on the home stretch. You can drop the 1 under and cross multiply. When we cross multiply, we'll have 100p minus p squared equals 900 e to the 0.01 t. This is as far as we got yesterday, or 2 days ago. Now we have to factor, and we have to do reciprocal, and we have a whole bunch more stuff to do. Okay, I want to fast forward through that. You don't have to do this on your homework, okay, do it because we've already done it in the proof. Look back on your proof from the day before. What does p equal? Okay, m divided by. Whoops. Okay, t. Oops. Mm-hmm.
And minus 1 also in the
Yep.
And as long.
Okay, so we can take now, I'm not going to make you go through that whole process all over again. We already did it. Okay, so we're going to jump from where we're at now to here by putting in what we know. So what do we know m is?
100.
M is 100. We knew that from the beginning, all the way back there where I pointed it out, that m was going to be 100. Okay, all right, e to the, what do we know that k is?
0.01.
Okay, we know what m is, 100 again, over p sub 0 minus 1 plus 1. So let's simplify. 100 over. Okay, what's 10 divided by 10 minus 1?
9.
So let's say it's 9. E to the negative 0.01t plus 1. I'm not going to make you redo that every single time. In fact, if it's a multiple choice question, you can go from here where you, no. I'll be even back farther. You can go from here, okay, where we know what m and k are, and you can fast forward all the way down and skip all of that and come all the way down to there. Okay? Because I don't want you to do this over and over and over again. Okay? Just get that far. So let me show you what I mean. Here's another one. And we're going to skip all of it. We're going to jump right to it because we've proved it already. I think of it kind of like when we proved the derivative of sine and cosine. We proved it once. I'm not going to make you prove it every single time. You know that the derivative of sine is cosine now. Okay? And so we're going to do the same thing with this now. We've proved it. Okay, all right, here we go. So here's another one. It's a population with a logistic growth rate dp dt equals 0.01p minus 0.004, oops, I missed a 0, 0.004p squared, and initial condition No, I'm not going to tell you the initial condition this time. I'm going to tell you the max capacity. Have you do it that way. 250.
Should we do an AP thing?
I've never seen anybody have to do it. Okay, so now we just got to come up with what P equals. So rather than separate and integrate, let's just factor and match it up. Because this is not in the right form. The form is supposed to be dp dt equals kp times 1 minus p over m. So I just need to factor so that looks like that. So what should I pull out first? I want it to be 1 minus. So what should I factor out? 0.01p, right? If I want it to be 1 minus, so I'm going to have dp dt. I'm going to factor out 0.01p. That's going to leave me with 1 minus what? If you factor out 0.01 out of 0.0004, it's just division. So if those decimals are, 0.0004 factored out by 0.01, you're left with 0.04p. But write it as a fraction so that it matches the form that we want. So have this be 0.01p. 1 minus, okay, what's 0.04 as a fraction? Okay, yeah, 1 over 25, p over 25. I think I missed a 0 when I copied my, I did. That's okay. We're going to fix it. We're just going to say the max capacity is 250. I copy on my notes. I have it's 0.1, and what I wrote down was 0.01. That's fine. Okay, now it's in the right form. Now you can tell what the max capacity is. You can tell what the K is. We just don't have the initial condition. That's what we need. Okay, so the last thing I have to give you is what the initial condition is. So now I will say that the initial condition for P sub 0 is 28. So we've got this is our K, this is our M, and we can jump right to P equals M over e to the negative KT times M divided by P sub 0 minus 1 plus 1. So we'll drop M as 25, K is 0.01, our initial condition is 28. So I have P equals 25 over e to the negative 0.01 t. The max is 25 over 28 minus 1 plus 1. Okay, this is a decreasing population. So P equals 25 over, so we have 25 over 28 minus 1, which is going to be negative 3/28. So negative 3/28 e to the negative 0.01 t plus 1. And now you have your population model. So this is going to be a logistic. Tom's pointing out the logistic is going to go like this. It's going to go down instead of going up like the last one did. The last one went up, and this one is coming down. So starting at 25 and then decreasing. Okay. You are also going to be asked to find, and we talked about this, the steepest point right there, okay, where it's decreasing the fastest. Okay, that's also the point of inflection. And so to find that point of inflection, you'll find the second derivative and set it equal to 0. Well, you already have the first derivative. Where's the first derivative? The original equation, right? Isn't the original equation the first derivative? So to find the point of inflection, we'll find the second derivative, and we'll set that equal to 0. Okay, so let's do that for this one. So dp, white. The first derivative, dp dt, was 0.01p minus 0.0004p squared. So d2, the second derivative, would be 0.01 minus 0.0008p. And I just have to set that equal to 0. So negative 0.0008p equals negative 0.01. So p is negative 0.01 divided by negative 0.0008. I get 12.5. Okay, so this is happening when the population is 12.5, whatever the population is. Population of rabbits, or population of bacteria, or population of whatever. Okay, the population is going to be 12.5 at that point, and that's when it is at its steepest. How do you figure out what the rate actually is? Because this is what the population is. How do you find what the actual rate, steepest rate is? What did you do with the 12.5? Plug it back into where? The first derivative to find the actual rate, and you'll get the negative number to show that it's steepest right there.